Good morning. We're going to get started here. Just about a minute or so to go. Give people a little bit of time to walk in the door. We're get going. Coming up, we have Alessandro Barbieri from Pluribus Networks giving us a talk on transforming lab automation with layer 1 fabrics based on SDN and white box switches. So we'll get started here in just a second. Appreciate it.
Give me a signal. Ready? All right. So good morning. Thanks for attending this talk. This talk is actually about lab automation, right? So who really cares about lab automation? Why, if you're here and you are an engineer and you're working in labs, you're responsible for rolling out new services, and you're constantly scrambling to patch and manually move cables and equipment in labs, then you probably have a problem that through lab automation can be addressed and resolved. Really, the business driver for lab automation is the ability to accelerate testing and onboarding of new services, building dynamically network topologies without having to patch manually, which is error-prone and definitely time-consuming. Another huge problem in labs is also equipment sharing. Typically, a very expensive traffic generators are siloed in different groups or organizations, and sharing this equipment is actually complex and difficult. Typically does not happen. That's why actually lab automation is relevant, really to increase the velocity and reduce capital expense and overall cut operational cost in lab environment. So I want to first review the basic concept of layer 1 switching. I'm sure everyone is familiar with it, but just to level set, a layer 1 switch effectively operates as a software-controlled patch panel. Once you can connect your routers or switches or traffic generators to a layer 1 switch, and the layer 1 switch effectively allows you to create circuits which can be dynamically modified through software, effectively a software-controlled patch panel. And to do that today, there are actually numerous technologies. Here I list the 3 most popular, but actually there are more technologies. There are packet brokers, derivative technologies. There are optical cross-connect, and there are media and optical media cross-connect, which also deals with electrical and optical interfaces. Overall, they do the job. Nothing wrong with any of this technology. However, you will find out as you actually try to implement this technology, the flexibility is not there. The ability to actually perform, operate in an environment with high availability, resiliency, also the ability to perform what I call here the DUT circuit sharing, or ability to effectively to, here, DUT circuit sharing, the ability to actually leverage multiple channels across, or a single channels across multiple DUTs, and even extend the layer 1 connection across labs or layer 3 networks, or even labs at different floors is actually not there. Those are typically chassis-based solutions built on custom technology, sometimes also very, very expensive. So what can we really do to improve the situation here? Another point that I want to make is that if you actually look at the technology commercially available from a layer 1 switching point of view, they really have a hard time to keep up with the explosion of Ethernet PMDs and PHYs and PMDs and the diversity of multi-mode fiber, single-mode fiber, copper, direct attach, multi-lane, single-lane. Very difficult to find this flexibility into an optical cross-connect, a layer 1 cross-connect, or even a packet broker. One thing we can do to actually start to change and improve on layer 1 switching technology is actually see if we can use white box, traditional white box technology. Those are commodity switches which operate, of course, their job is not to perform layer 1 switching, but perhaps we can emulate a layer 1 switching with a white box. If we do that, Just because we use this hardware, immediately we get all the flexibility in Ethernet interfaces. From 1 gig, 200 gig, 400 gig, 100 gig, immediately you get the benefit of having a platform which scales nicely, effectively with your network, because effectively it's the same device you can use in your network. We have full ability to convert a single mode fiber connection into multi-mode fiber, copper into fiber, mix and match all this connection, and even speeds. You can connect a 1 gig port to a 100 gig port and still have effectively layer 1 emulated connectivity. Because these white boxes are normally 1U, 2U at the most, you can actually build a very large scale-out fabric through leaf and spine architecture, and you can accomplish, let's say, scale capacities which are at least an order of magnitude higher than a traditional layer 1 solution. I'll show you a couple of examples in a moment. And while you do all that, you can dramatically reduce the cost of building a layer 1 switching fabric for your lab compared to traditional technologies. So I want to show you now the most interesting part. Yeah, the white box is interesting. It's actually very powerful in terms of hardware platform. But there is software that can also take advantage of this platform and perform what I call it a layer 1 emulation. Of course, you're dealing with a packet switch platform, and you're trying to emulate a circuit switch technology. I call it here for simplicity virtual wire, because effectively we're not really pulling wires like you do in a physical, let's say, cross-connect or in a physical layer 1 cross-connect. What we're doing here, we're emulating virtual wire. And I'm going to propose 2 approaches. One is extremely simple. One is more complicated in terms of implementation, but it's a lot more flexible and, frankly, a lot more interesting and exciting when it comes to building a next-generation lab automation. So one is based on the white box hardware. I'll show you how it can be done. And the other is based actually on an IP plus an overlay type of technology. So you end up encapsulating all your DUT device under testing traffic on top of an IP overlay with some interesting properties. Let me walk you through the first example, the first scenario, using a basic white box. And then what you do here is actually pretty simple. This is, let's say, a sample pipeline of an ASIC, a merchant silicon chipset. You have your tunnel termination, your layer 2, layer 3 lookup. You typically have an ingress ACL tables. You have a metering functionality, buffering, et cetera, egress ACL. This is the full pipeline. The trick here to emulate a circuit switch using a packet-based technology is to disable most of these blocks. So the software is supposed to disable, turn off most of these processing blocks in the pipeline of the packet. So what we do in the software, we need to disable, number 1, MAC learning. Second, you want to disable any layer 3 routing and switching BPDU kind of processing. On top of it, you need to prevent the CPU of your switch to receive any packet from the network. So the entire control plane processing needs to be turned off. And all the switch is supposed to do is program for port 3 to be connected to port 10, is to program effectively an ingress ACL. And this ingress ACL has a very simple rule, which says associate all the traffic coming from port 3 to port 10. And because you have disabled all the rest of the processing, you effectively have already emulated a layer 1 switch. It's a nifty trick which allows you actually to use a white box as a true, let's say, as a quasi layer 1 switch. Of course, there are limitations which I'm going to discuss later on, but at a high level, this covers probably 95% of the use cases. Also, I want to point out that at least the devices we experimented with allows you actually to turn off error frame processing. So you can actually transport CRC packets, CRC error frames, Ethernet frames. You can also transport RAN packets, small packets. So you can really emulate a true wire in terms of transparency even to packet errors. And last but not least, I want to point out something interesting, because this is what actually layer 1 switches do. When port 3 goes down because you disconnect the DUT, you're supposed to send a signal to port 10, and port 10 gets disconnected. That's what happens when you open a circuit. Well, in this case, your software needs to, the software running on this white box needs actually to perform this operation of effectively propagating a link failure or a link up-down event to the remote port. So this is a couple of examples of what you can achieve with this. You can achieve full transparency to any Ethernet packets. You have error frames at the top, control packets at the bottom. You can have LLDP packets, BGP, LACP, and different Ether types, even MPLS, fiber channel over Ethernet. All sorts of encapsulation Ether types actually can transport it across an infrastructure program the way I described before. Also, very interestingly, from a flexibility point of view, you can actually have a 100 gig port talk to a 10 gig port, a fiber connected to a copper. All these combinations are now possible, and many of those things are not possible actually with traditional layer 1 cross connects. This is an example you can build easily with a 1U switches, with a 1U switch with 32 ports of 100 gig, which splits into, each port splits into 4x10 or 4x25. You can easily build a non-blocking fabric with 2048 ports with 16 spines and 32 leaf switches. So the scalability is actually pretty significant. Just want to show this as an example. So in a nutshell, what do you get if you use a white box with a few tricks in software to emulate a layer 1 switch? What you get is a device which is transparent to all kinds of Ethernet traffic, encapsulation, including errors. You get a device which gives you enormous flexibility in terms of mix and matching Ethernet interfaces, any speed, any media conversion. If you're lucky, you get an OS that implements the logic to track effectively the state of a port across the fabric. So you can disconnect on leaf 1 the DUT that is connected to leaf 25, and leaf 25 is supposed to receive a signal that this device, the device has to be disconnected, or there's a link up and link down event. This infrastructure is normally programmable, unlike traditional layer 1 switching. You can use modern REST API, Ansible style automation to actually program this kind of infrastructure. And you also have the ability, if you implement lab automation software, there are a few companies building lab automation software, they give you the ability actually to do end-to-end path discovery across a massive leaf spine fabric. And last but not least, this is a modular pay-as-you-grow design. You can start with 1 device, going to 3 devices, and so on. It's truly modular pay-as-you-grow, unlike a traditional large, let's say, layer 1 switching matrix, which typically come in a chassis form factor. The second more interesting way, a more disruptive way of thinking about building a layer 1 cross-connect fabric is actually by implementing what I call here a point-to-point virtual private wire service. I'm actually reusing, borrowing language from this EVPN RFC, which actually defines how to build a point-to-point transparent link across a BGP and a BGP IP underlay effectively. So here again, what you do is you have your leaf switches connecting to your devices under test. Here you can have your core spine. It doesn't really matter actually what you have up here. This is pure transport of IP packet at this point. And you build effectively an underlay with IP, CMP, BGP. Then here the goal is to build an overlay where the virtual tunnel endpoint sits on every switch, and it allows you to actually create a mesh of tunnels between all the leaf switches. In this case, you can use an EVPN control plane to manage all this. That's an option for sure. But really the key here is having software which can hide all this complexity, right? Because in the end, you're in a lab, you want this to happen pretty much with a point-and-click operation. I'm just disclosing under the table what really is happening under the hood, what really is happening to this infrastructure. But you're managing this infrastructure with the same software that you use to manage a regular virtual wire. The trick here, again, to disable MAC lookup, no learning. You want these links to be transparent to every protocol. Failure propagation is also very desirable here, is actually a must, and it's actually implementable if you look at this technology specified by EVPN. Now, the problem is there are very few implementations today, and even less are integrated with lab automation software. But this actually gives you the full benefit of an IP ECMP fabric applied to lab automation environment to build a dynamic cross-connect, layer 1 transparent cross-connect. So, in this second scenario, what you get on top of everything I discussed before, you get actually 3 or 4 interesting properties. Number one, and I will actually show you what I mean by that, you have the ability to have guaranteed path automatic discovery between any two DOTs. In a traditional circuit switch environment, even if you provision a fabric with non-blocking bandwidth, I will show you that you can actually end up in situations where you do not have the guarantee ability to discover a path between any two DOTs, which is actually very disruptive. Second, we have the ability to perform dynamic bandwidth utilization. So what this means is you can connect 40 DOTs and leverage one uplink. In a circuit switch environment, 40 DOTs, you need to burn 40 uplinks. So it's a lot more efficient, and you can actually share fabric paths in the fabric, in the ECMP fabric, across multiple DOTs. Then, path resiliency and automatic failover. If a spine fails, if a link fails, you rely on an IP fabric to reconverge, right? You have sub-milliseconds reconvergence. It's transparent to the DOT. The DOT will never experience a failure. If today you try to deploy a layer 1 switching fabric, even with fancy orchestration software, if there's a failure, the DOT is down, somebody has to go in and find another path through the fabric. It's very time-consuming and expensive. The way around that, typically I've seen people over-provision the fabric uplinks to have more paths available to reduce the occurrence of failures and oversubscription. Then the last important properties we are adding, again, now we are leveraging an IP transport, right? So these layer 1 circuits are actually traveling on IP. At this point, I have multi-location capability. I can extend this technology across labs. This is unthinkable, of course, in a traditional layer 1 cross-connect technology. Now I can connect 3 labs, 5 labs, 8 labs through this technology and share resources across multiple labs. Very, very powerful. Of course, because now we are encapsulating using VXLAN, there's a sort of we need to be mindful that all the routers in the path connecting the geographically distributed locations must be able to accommodate the MTU adjustment from VXLAN. It's about 50 bytes, okay, extra. So the MTU needs to be factored in. The disadvantage of this technology is that, of course, you're managing an IP control plane. It's not as sort of simple as, let's say, the basic layer 1 switching, but that's also why it's a lot more powerful. Again, the trick, I repeat, if you have integration with lab automation software, which can be homegrown or can be, there are 3-4 companies actually building these solutions, then you don't really know you're running an IP network underneath. It's all taken care, all automated. You just have to decide which port connects to which port dynamically. Now, let me actually review the 4 advantages of this technology using over a traditional layer 1 switch. This is actually what I call layer 1 path auto discovery with guaranteed connectivity. Here, let's say you bought a traditional layer 1 fabric, right? And what you have here is you have 6 ports down, and then each device has also 2 uplinks. So this is actually non-blocking. Technically, in networking language, this is a non-blocking architecture because you have equal bandwidth leaving the switch as you have serving the devices under test or the edge ports. Now, look at this. A connects to B, right, through the blue path. C connects to F through the green path. And now you want to connect the B to E. Well, B can go here, but has no way to reach E. So although you have bandwidth, and this is technically, or let's say, a known block in fabric, you end up in a situation with just 6 ports, you cannot find a path. This is actually where people building these things typically over-provision by a factor actually of 2. So the cost explodes. Of course, it can be done. It can mathematically resolved. But the cost of doing this is in complexity and dollars because you need to proliferate number of spines, number of cables, and this is a big problem operationally, right? You cannot afford to have, although you have bandwidth, not to be able to connect to DOT resources. Very disruptive. Now, let's consider the case where we have an IP fabric underneath with our overlay technology on top, with all the tricks and modifications we have done. At this point, A, B, C, D, they will always talk to each other because effectively you're using a packet multiplexing here. You're not building static circuits, carving static circuits like you do here. Here is packet multiplexing. You always find the path to destination. Always find the path to destination. And by the way, this path is completely auto-discovered. You don't need to in this case, you need software to engineer which uplinks you take to reach the remote leaf and the remote DOTs. Here, you let IP figure it out yourself. You just say that you want to connect port A to port E, port C to port F. Any combination is fair game. You let IP then do the job for you. It's extremely more efficient and extremely simpler in the end and lower cost to implement because now you can leverage. You don't need to over-provision to avoid, let's say, path conflicts. Another important point here is the ability. This is actually another massive difference, right? Imagine you're building a fabric like this, right, with a traditional layer 1 switching technology. You want to connect 2 DOTs. The uplinks are 40 gig in between because you may also have 40 gig devices. Well, in this case, because you need to carve out a circuit end-to-end, you're burning a full 40 gig path to transport 1 gig. Not great. Here, we leverage, again, IP packet switching. So you can have 41 gig ports, ride a single 40 gig channel. Again, this is a much more efficient way to utilize your assets, your links, and effectively you reduce dramatically the number of devices you need to manage. Path resiliency, right? And automatic failover. Like I said before, if your DOT fails or a link fails or a spine fails, anything in the path fails, you're done. It's all about figuring out manually how to reconverge. An operator needs to go there and try to find a new path through this fabric, right? It can be automated all you want, but it's a lot of work and it's manual, right? Here, you leverage effectively ECMP, right? A link goes down, a spine goes down, 2 spines go down, doesn't really matter. The connectivity is always guaranteed between two devices. So for 90% of the scenario, 95%, this is actually a solution which is very effective, and you can't do those things with traditional virtual wire or traditional layer 1. This is my favorite, frankly. It's the ability, because now we're leveraging an overlay technology. An overlay technology means you are routing effectively tunneled traffic, so those are UDP packets. I can actually now interconnect the location across any WAN. You can transport IP, then you can transport my layer 1, let's say, circuits, virtual circuit, emulated circuits across multiple locations, and you can share equipment and build a logical topology with equipment which is geographically dispersed across multiple labs. This is sort of a summary of what I discussed today, right? So on the first column, you have the traditional layer 1 technologies. Here we have the virtual wire done with white boxes, and here we have the virtual wire done with an IP overlay. I call it the layer 1 plus. The layer 1 plus clearly gives you the best flexibility, right? You can do automated path discovery, path resiliency, dynamic bandwidth sharing, extend across locations. What you cannot do that easily is actually error transparency. This is actually chip dependent, hardware dependent. Some chips allow you to disable CRC, but actually small packets are very hard to get through in an encapsulated VXLAN scenario, at least for the investigation and analysis we have done. So a little bit of limitation, and plus, if you're conducting wire speed testing, let's say you are a network equipment manufacturer or that has to test high-speed interfaces, then you need to factor in that there's an overhead due to this encapsulation. You don't occur into any overhead in any other technology. The virtual wire, compared to traditional switching technologies, is a lot more flexible in terms of mix and matching interfaces and densities and cost and scale-out capabilities of the fabric you can build, but effectively is a little bit more intelligent version of a layer 1 device. What you cannot do with a switch like this, with a white box, for example, is transporting Ethernet backplane, let's say KR type of interfaces, KR, KX interfaces. Because in the end, here is not a layer 1 switch. It's still a packet device, and you're just emulating through the tricks I've shown you before. You're emulating a layer 1 circuit. So it's not truly layer 1, and you lose a little bit of transparency. But again, we're talking about 80, 90% of the applications for which actually this technology can easily replace traditional layer 1 switching technologies. This is the end of my quick talk. I want to open it up. I have 4 minutes. If there are any questions, happy to take on your questions. No more questions? Okay, thank you.
All right, thank you very much. I'll be just a few minutes here. Coming up is a talk from Jeff Houston. So give me just a couple minutes and we'll get that going. Thank you again, Jeff, for that great presentation. So we are a little ahead of schedule, not too much, just getting mic'd up and we'll get moving to the next one. Coming up, we have a
Is there a clicker?
Yeah, it's right here. This one right here, sorry.
Oh.
So, slides forward, slides back.
How do,
Laser pointer.
how do I like play something if I have like a video or something like that?
Was it embedded?
It was embedded.
Let me find out.
Okay.
That real quick.
Okay. Should I just wait for you? Should I wait for you before I start?
Yes.
Okay. Hey guys, I think we're gonna get started here. So this talk is called New Data Architectures for Network Flow Analytics. And before just jumping into the talk, I want to give you guys a brief introduction of myself. My name is Fanjin. A lot of people call me FJ. And I'm a co-founder of a technology company based out in the Bay Area called Imply. And actually prior to the startup world, I spent most of my career in building highly available, highly scalable distributed systems. So this talk will actually focus a lot on my experience on working with network flow data and building out different types of databases and data systems for network flow data. So just a brief overview of this talk. What I'm going to be covering is really some of the problems I see today with network flow analytics. I'm going to be talking about different technologies that can be used to solve some of these problems. I'm going to be talking about a class of databases, a new class of databases called operational analytic databases. And I'm also going to be talking about an open source project called Apache Druid, which is something that I work on that's going to relate to this whole idea of operational analytic databases. Then I'm going to be going into details about the architecture of how these operational analytic databases work and how can they be deployed in practice. And at the end, we'll take a few questions as well. So just getting started, I'm going to start with some very high-level problems, and then get into increasingly more detail, more sophistication around some of the problems I've seen with network flows. So very high level, I think we all know this, network flow data continues to grow in scale and complexity today, especially at major enterprises. More applications are being deployed on the network, and it's very, very critical for analysts, operators, and even monitoring teams out there to understand the performance of their network and also to be, as quickly as possible, able to troubleshoot issues in the network. So this data, it can be flowing in real time. A lot of operators are working with live data about their network, but historical data is also important as well in order to understand anomalies, in order to understand problems in the network, especially what's happening right now. You have to understand what has happened in the past. So talking very broadly about the data, flows, they can come in many different forms. You can have net flows, F flows, IP fix, et cetera. Network data can oftentimes also be enriched with application level data, so information about the types of applications running in the network, as well as user data, so what types of users are using what types of applications. What's pretty common with network flow data that I've seen is there's really three types of components to this data. So one, there's a timestamp, and this timestamp indicates when the flow is created, when it occurred, when some event occurred. And then there's a set of attributes or dimensions. So these are properties that describe the flow. These are things like your source address, source port, destination address, destination port, and so on and so forth. So attributes or dimensions are things that you would group on as you do your analysis. And most of the time, as part of your analysis and part of your data, you also have a set of measures or metrics as well. So these are the numbers you actually want to crunch as part of any sort of analysis with network flows. So these are things like just a number of flows, it could be a number of packets, it could be bytes per second, it could be quantiles and histograms on performance of the network, and so on and so forth. So measures are usually numeric things that you want to crunch, and dimensions are things that you want to group on. So the use case with network flow data, as I mentioned, very high level, we want to be able to monitor the network. We want to be able to proactively detect issues. And when issues occur, we want to resolve them as fast as possible. Going into more detail about what does it take to resolve issues with flows, what does it take to resolve issues in your network, usually the types of queries that are made on top of this flow data tends to be rank in order. So for example, for a given destination address, I want to see the top sources addresses that it came from. Or it could be a lot of different types of top ends on various attributes of the network. A lot of queries also involve search and filter, so perhaps you want to be able to resolve issues on a particular subnet address or on a particular single IP address. So for the system used to power these types of queries and to be able to answer these types of analytic queries, we want our analytic system in general to be very cheap, very efficient, because there's a lot of network data and we don't want to spend that much money on hardware. Okay, so before kind of just jumping into data architectures and jumping into and classifying different types of systems, I thought I would just go through a video of a very quick demo just to showcase what it means to diagnose something interesting within network flow data. And this is really just to provide context for the rest of this talk as we start going through different types of architectures. So this video and this demo is really just about UI that's being used, that's being powered by some of these data systems I'm going to be talking about a little bit later, and how this UI can be used for solving different types of problems with flow data. So I don't know if there's actually any sound with this video, so I'm basically just going to kind of commentate over what's happening here. So this is a UI describing flow data. This is actually live data that's coming from Imply's own network. And our infrastructure is actually being entirely deployed in AWS today. So on the left-hand side, you see those dimensions and attributes of flows I'm talking about, like the interface, the action, source, destination address. On the right-hand side, we have various types of measures. In this example right now, we're really just looking at like a count of flows. And at some point, I'm going to actually, I think when I recorded this video, I'm going to start dragging and dropping different attributes into the center and going through a workflow of basically diagnosing and understanding why traffic is getting rejected in our network. But right now, I think so if you see on the right-hand side, it's just a bunch of different types of measures or metrics related to flows, things like bytes, bytes per second, bits per second, percentage of traffic that's accepted or rejected. And with any good kind of network flow system, we want to be able to slice and dice these metrics based on the dimensions and attributes of the data. So here, what we're looking at is we're just looking at a count of flows over the latest hour. There's various other views we can look at. We can look at maybe the latest 6 hours, latest day. By dragging action to the center, what we're looking at are the actions that are happening actually in our own internal network, which percentage of traffic is accepted, which percent is rejected over the last hour. And I believe what I'm going to do now is actually just filter in and really look at the rejected traffic. Because as you can see here, there's a non-trivial set of flows in our network that's being rejected. So the immediate question that comes is why? Why are so many flows being rejected? What's the cause of it? So one of the things we might investigate right away is the destination port in which the rejected traffic is happening. And what we can actually see here through this UI is most of the rejected traffic is actually happening on port 6379. And maybe we actually want to understand on port 6379, what are the top destination addresses in which flow traffic is getting rejected on. So here we see a particular IP in our network is where the vast majority of rejected flows is coming from. So we can actually search, filter, and focus entirely on this IP and look at the service name of this IP, in which in this case it's an unmanaged service name. Next thing we want to do, knowing that a given IP is where most of the rejected traffic is coming from, is look at the sources of that traffic. So in this case, what we see is actually two IPs generating extremely uniform traffic. So these two sources just comparing their traffic, it looks like both of these source IPs are generating extremely uniform traffic against one of our destination addresses, and we're rejecting all of that traffic. So the workflow that I'm trying to showcase to you right now, and the workflow that I want to be talking about a little bit later on, is this one of being able to arbitrarily slice and dice flow data and really start examining it based on an arbitrary set of attributes to try and understand why rejected traffic might be happening. So in this case, what we see is there's two IPs that's issuing live traffic to one of our destination addresses. We're rejecting all of it. We're looking at this traffic on a minutely basis, and it seems like actually every 3 seconds, one of these IPs is issuing a request. So this clearly seems like automation against one of our internal servers. And actually looking into what these source IPs are, these are actually like Amazon servers, which is kind of interesting. So it's probably some other organization that's deployed in AWS trying to connect to us. But hopefully that gives you an idea of kind of the analytics workflow, the exploratory workflow, the investigative workflow that we want to start doing with flow traffic. So some of the challenges of being able to investigate flow traffic and understand why certain things are happening, why trends, patterns, or anomalies are happening. Some of the challenges are just around the scale and infrastructure required to handle the data, and some of the challenges around enabling very fast investigative queries on the data. So looking at flow data today, if you're a pretty large enterprise, if you're dealing with a non-trivial set of flow data, you're probably dealing with millions of events per second. And most of this data is coming in real time. However, you might have a bunch of historical data about your flows as well. This data, as I mentioned at the very beginning, is becoming increasingly complex. So complexity really relates, in my world, in my mind, to dimensionality and cardinality. So dimensionality is about having many different attributes in your flow data. So everything about the interfaces, everything about the source destination ports, and potentially enriching this data with application information as well. Cardinality is this term to describe the number of unique values kind of within a single dimension. So if one of your dimensions is IP address and you have millions of IP addresses and you want to rank them on some particular metric, that can be a very complex, very difficult operation to do if you have a lot of unique IP addresses or a lot of unique values within a single dimension. Another one of the challenges of working with flow data is just around the structure of the data. So more and more so, flow data is becoming unstructured. It could be arbitrarily nested. You could have JSON blobs which don't have a predefined schema to them. The events from time to time are evolving and constantly changing. So your schema from 1 hour to the next hour might be very different because you're seeing very different types of events. So these are all challenges around both storing and computing kind of the base flow data that we're working with. Now, in terms of accessing the data, more and more so, people are not issuing SQL queries, they're not issuing programmatic queries against the data. People are leveraging UIs to investigate and understand flow traffic. So a good UI needs both reporting and exploring capabilities. And to leverage the UI in order to do troubleshooting, you have to have very fast search and filter, you have to very fast drill down. And this allows you to very quickly slice and dice the data to pinpoint various issues within your flow traffic. And then the last kind of challenge with UIs in general is in most enterprises I see today, there's really kind of one central team that's providing flow analytics out to many different other teams that require this data. So there's this idea of multi-tenancy in UIs, which is being able to support potentially thousands of concurrent users trying to access the same data at the same time. Right, so to solve these challenges, to really build a system that's great for understanding flows and for troubleshooting and investigating issues that we see in flows, there's a lot of different technologies that we consider. And there's kind of 3 broad classes of technologies that I see the most oftenly deployed. So these technologies are log search systems. So this is the ELK stack. These are search systems such as Splunk and other systems in that category. Another data system I see often are analytic query engines. So sometimes these are traditional analytic databases such as Vertica. Sometimes there are new SQL Hadoop solutions such as Presto. And then the last set of technologies I see commonly deployed are time series databases. So systems such as OpenTSDB, Prometheus, and InfluxDB as well. And I'm just going to actually talk about some of the advantages and disadvantages of these different types of systems, and then discuss this idea of operational analytic databases, which is a new architecture that's potentially, in my mind, solving some of the issues that we see with these three legacy classic approaches to handling flows. So the first set of systems are log search systems. So this is very commonly, I see this used with network traffic, so the Elk stack and also Splunk as well. Some of the major advantages of systems like Splunk and Elasticsearch: one is they're very good at doing real-time ingest, so you can feed in live flow traffic. They're very good for being able to handle semi-structured and unstructured data, so you can have arbitrarily nested blobs of JSON and Avro and other data formats you can just kind of feed into these systems. And then they're also very good at fast search and filter. So investigation in flow data oftentimes requires very fast search and filter. The problem that I usually see talking with different people that use these systems is around performance. So one, systems like the Elk stack and Splunk, they're not the most performant when you have high-dimensional, high-cardinality data. So if your flow traffic doesn't have 5 attributes, if it has 50 attributes, if it has 100 attributes, and you want to group on, rank, sort, and order all of these different attributes, you want to slice and dice across all these attributes, then a lot of these log search systems start really slowing down in terms of performance. Another drawback I've heard often around log search systems is their performance for numerical aggregation. So if you're just crunching the number of flows, maybe you want to count the number of unique devices that are available in your network, or these types of queries that require adding a bunch of numbers together. This is fundamentally not what the Elk stack, fundamentally not what systems like Splunk are designed to do. They're really designed for search and filter, and not so much for metric aggregation and crunching numbers. So what is designed for very fast analytic queries that involve crunching numbers are what are known as analytic query engines, or OLAP systems. So systems like Vertica, systems like Presto, even more old school data warehouses like Teradata. And the way that a lot of these databases work is they have a column-oriented storage, which makes them really, really good for crunching numbers. They're designed to support large, complex group bys. They're designed to support all different types of complex aggregations. So you can build histograms, you can build quantiles, you can calculate rates of a lot of different types of flow traffic. The main drawback of a lot of analytic databases actually are probably on the ingest side. So they're not really designed for real-time ingest, so they're not really good for streaming and flow traffic. They really require DBA to start designing schemas. So if your flow traffic has nested JSON or has an evolving schema, these types of systems are not really built to deal with changing schemas. And the final thing is most analytic query engines, things like Presto and Vertica, are very slow for search and filter. This means that if you want to start doing investigation by ad hoc analysis of your data, this is not a super great fit. Last set of databases here that I see starting to get more popularity are systems such as Prometheus, InfluxDB, or OpenTSDB, which are time series databases. And the way that time series databases work is that they're very, very efficient for adding numbers and then partitioning and filtering on time. So time series databases have time-optimized sharding, they have time-optimized storage, and then you can aggregate metric values extremely quickly. The main drawback that I've heard with systems like Prometheus and InfluxDB is that they're very slow when you start grouping, ranking, and sorting on your dimensions, which are not time. So if you want to look at a given source IP and then all the destination IPs that feed into that source IP and maybe all the interfaces across all those destination IPs, this is a 3-level multidimensional group by. This is something that time series databases are not really designed to do because it's a pretty complex analytic queries. And then the other drawback of time series databases is they're not great for search and filter. So as you start doing more investigations, they're not great for fast slice and dice. But what I want to try and highlight, why I talked about 3 different classes of data systems, is each of them has attributes which make them really ideal with working with network traffic data, with network flow data. And really recently, we've seen a new class of data system that's starting to emerge. Then the whole idea behind this class of data system is trying to combine ideas from time series databases, from analytic databases, and also from log search systems as well. And this new class of data system is designed to try and remove all the cons of these three types of databases and merge all the pros together. So I don't think there's an industry standard term for this class of database yet. However, I'm going to kind of make one up and call it an operational analytics database. And the whole idea behind this new class of systems is trying to combine the benefits of time series, analytic, and log search systems. So this new class of database, what it can do is it can provide the ingest and the search and filter capabilities of systems like ELK and also Splunk. They store data fundamentally in a column format, similar to Vertica, similar to Presto. So the idea is you can have all the query and analytic capabilities of some of these analytic query engines. And then these data systems also have time-specific sharding, time-specific optimizations, similar to systems like Prometheus and also Influx as well. So the overall idea is we can do the best of all three worlds. So there's a bunch of different types of operational analytic databases. At one point in time, there's really only one, but now I would say there's 5 or so that I hear about pretty frequently. I'm one of the committers on Apache Druid, so I'm obviously very biased in that I think it's the most popular operational analytics database out there, and a lot of this talk is going to focus on the architecture of Druid. However, there's Scuba at Facebook. So for folks that work at Facebook or may have interacted with Facebook, Scuba is an example of an operational analytics database that's used for all different types of workloads at Facebook. There's Pinot that's coming from LinkedIn. There is Paolo, which actually I think is now called Daisy, that's coming from Baidu. And then there's ClickHouse, which is made by the Russian search engine Yandex. Basically, these 4 or 5 systems architecturally are virtually identical. They all have the same ideas. They all combine ideas from these legacy systems. Their storage formats are almost identical as well. So how they store data, how they query data, their fundamental architecture is very, very similar. So I'm going to talk about how these operational analytics databases work, but I'm going to be using Druid as a case study because 1, it's an open source project. It's incubating in the Apache Software Foundation, and 2, it's because it's the one that I have the most experience working on, and I understand the architecture the most deeply. So Druid runs in production at many different companies of many different sizes. I just put up a couple of links that you can find on the internet about how various people are using Druid. It is very, very commonly used for network traffic, network flow analysis, and investigation as well. So how does Druid store data? So let's look at some raw data right now. This might be just some raw flow data, so there's a timestamp of when the flow occurred, and then just for simplicity's sake, there's only 2 dimensions. There's an action, which was the traffic accepted or rejected, and what was the sort of the protocol of the flow, and then just a count of flows for a particular period in time. So the first thing that Druid actually does with the data is a pre-aggregation or summarization step. And in the summarization step, what Druid is going to do, and this is something that's optional, is it's going to truncate the time in which raw data appeared at, and it's going to try and find commonalities basically in the dimensions of the raw data. So in this case, we're truncating data to an hourly granularity, and you can see that once we truncate the timestamp, basically there's a bunch of different rows that have the exact same set of attributes, and what we can do with this flow metric is we can just aggregate it together. And this in practice can be very good at reducing sort of the raw data you actually end up storing in the system. What you trade off is information about the time in which events occurred, but what you gain is potentially a lot of storage savings and also performance improvements as well. And in this example, we're not losing any fidelity of the data, so this flows metric is still going to be accurate for the given timestamp. The next thing that Druid and all these operational analytic databases do is they partition data by time. So this is how every time series database works, and this is how Druid works as well, where once we roll up the data, then we look at, can we split this data up by time in some meaningful way? So in this example, what we're actually doing is we're partitioning data based on hours. So every shard of data, every partition of data within Druid is representing an hour's worth of flows. In practice, each one of these shards or segments is containing millions of rows of actual data. But this level of partitioning allows us to do very quick queries based on time. So if we're only querying for an hour's worth of data, we don't need to hit all these other shards. We can actually just find the shard that contains the hour's worth of data that we care about and only scan that data. So it's one of the performance improvements of our operational analytics database. So these shards or segments in Druid, they are a very fundamental storage unit. They're basically immutable once they're created, and they're designed to be very read optimized. So we don't have this contention between reads and writes. Basically, once a segment is created, it's designed to be read as fast as possible. And the parallelization model, how an operational analytic database actually scales is you have kind of one thread allocated to one segment at a time. So when you add more CPUs to your cluster, you can scan a lot more data in parallel. So I talked a little bit about how Druid looks like a time series database and how it partitions data based on time. This is really about how Druid looks actually like an analytic database in that it stores all attributes and all dimensions fundamentally in columns. So column stores in the analytic database world are known for being able to aggregate numbers very, very quickly. They're also known for being very good at compressing different types of attributes. So in this case, this is an example of something called dictionary coding. The idea is in our flow data, we might have an action dimension and a protocol dimension, and we might have two values for action, accept or reject. And as opposed to storing these variable length strings directly, we can actually assign an integer value to each string. So accept gets assigned to a value of 0, reject gets assigned to a value of 1. And in terms of the protocol, TCP might get assigned to a value of 0, UDP gets assigned to a value of 1. So when we actually end up storing this data within our database, we're not storing these raw strings. What we're storing is integer encoded IDs. And then there's a lookup between the integer value and then the string value. And in practice, especially when you have a high cardinality dimension with a lot of string values, this can result in significant storage savings. One other thing here, so Druid also looks, in all operational analytic databases, they also look in part like a search system, so they look a little bit like ELK as well. And the idea is that we can create different types of search indexes for very fast search and filter. So in this example, basically we have our action attribute, which has two values, accept and reject. We can actually create a lookup which tells us in which rows the accept value is seen and which rows the reject value is seen. So accept is seen in rows 0 and 1, so we can build this binary array that basically, so we have a laser pointer here, that basically indicates that accept occurs in these two rows and doesn't occur anywhere else. Reject only occurs in these 4 rows and not anywhere else. And the idea is when we issue a query just on all of our rejected traffic, we don't have to scan through all of our data. We can actually just look at rows 2, 3, and 4 and add up the number of flows in those rows. And this is something that all search systems do for very fast search and filter, for very fast investigative analysis. And similarly, because with these binary arrays indicating where values exist or don't exist, we can do Boolean operations over them to basically indicate which rows contain either the accept value or the reject value. So in this case, it's actually every row. And of course, a lot of these indexes can be compressed as well. Kind of one last thing I want to talk about related to storage is approximation algorithms. Many aggregations in the network flows world don't quite require exactness. So for example, count distinct, histograms, and quantiles, and different forms of set analysis. You don't have to do these exact anymore. Most of the time what people are looking at are general patterns or trends to see if the changes or the deltas are actually meaningful. And because we don't need exactness always, then we can start leveraging approximation. And approximate algorithms can be very powerful for providing fast queries while kind of reducing the storage requirements. And just kind of give you an example here. So this is how Druid does rollup. I talked about this a few slides ago. If we were to enrich this basic flow data with a device ID, so maybe we want to understand all the devices running our network, and we have a lot of unique devices, this basically prevents our ability to roll up the data and really get those storage and performance benefits. So as opposed to storing every single unique device ID, we can actually store an approximation of the number of unique devices that we've seen. And this is something very powerful, where we actually convert device ID into an approximate metric that allows us to roll up our data again. And this allows us to get all the storage and performance benefits of having a smaller, reduced data set. Okay, just going into the architecture of these operational analytic databases, pretty much, Scuba, Pinot, ClickHouse, Druid, all of these architectures are pretty similar. The architecture of Druid is that of you can think of it as kind of a disassembled database. So there's different types of processes, and each process can be kind of fine-tuned depending on your workload. And the idea is you would have some raw data either in a file system. The raw data could be a stream of data, it could be collected, it could be something in Kafka. And what Druid is going to do is it's going to convert raw data into this optimized partition segment format. So the segment I talked about a few slides ago is this column-oriented storage with search indexes built in that's time partitioned. And that's the thing that Druid is fundamentally working with for all queries. So you have raw data that's getting converted into segments on an indexing process, and then these segments are loaded across a set of historicals, and historicals are processes that are basically designed to read segments, and that's pretty much all they do. And then you have a set of processes called brokers, and brokers are responsible for kind of query, scatter, gather. So the idea is queries will hit a broker. Brokers know which segments are getting created live on the indexers and which ones are already completed and living on historicals. So brokers do query, scatter, gather. These guys kind of crunch their portion of the answer in parallel and then return results to the query broker. And then the broker unifies all results together. And then how do you actually query these things? There's JSON over HTTP, SQL, R, Python, Ruby, pretty much whatever language you're comfortable with, you can actually query Druid with. So by the numbers, most of these operational analytic databases are designed to scale to, they're all designed to be horizontally scalable. They're all designed to deal with some pretty tremendous volume. Druid in particular has a lot of public information about some of the size of the clusters out there. So some of these clusters are now at 100 trillion raw events, ingesting more than 300 billion events daily. And even on clusters of this size, there's average query latencies of about half a second. So really, when your query latencies become less than a second, you can start doing really fast slice and dice queries through a UI. You can start really exploring, doing ad hoc analysis of data. And this is, I think, very important in the NetFlow world. And some of these benchmarks were presented on a data set that has about 30 dimensions or 20 metrics, which is similar to what you would see with NetFlow data. So the last thing here is just kind of end-to-end architecture. Where would you deploy an operational analytics database? How does it fit into a modern data stack? So the modern data stack that I see most common within the enterprise today is one where there's really dedicated systems for dedicated workloads. So the most common thing is you would have raw events that get created somewhere, and then they're either collected through some sort of collector, and then they're fed into a message delivery system known as a message bus. The most popular message bus I see is probably Apache Kafka. I see a lot of NetFlow data go through Kafka today. There's other message buses in Amazon. There's AWS Kinesis. There's Google PubSub, and I think Microsoft has their own thing as well. So the next stage after data is kind of collected and being delivered to the message bus is through some sort of data processing or ETL system. In the NetFlow world, the most common path is through some sort of stream processor. So the idea behind the stream processor is to enrich the NetFlow data, to add things like application information, potentially adding user information as well. So the stream processor, popular systems out there include Apache Flink, Apache Samza, Kafka Streams. They're all designed to do the same thing. They're designed to transform and enrich underlying raw data. And then finally, where the enriched data ends up is in some sort of query layer. So in this case, it's going to be Druid. So the end-to-end architecture looks like I collect flows from somewhere, I put it into Kafka. Maybe from Kafka, I'm going to deliver it to a file system. Maybe I'm going to deliver it to my ETL layer. And then I'm going to put it into a serving layer where my queries or where my users are interact with it, where my applications are going to start talking to it as well. So Druid being an open source project, it really works out of the box with a lot of other open source projects as well, and we're really big believers in sort of a more disassembled data stack nowadays. So Druid works out of the box with message buses like Kafka, Kinesis, Google PubSub. It works with file systems like Hadoop, S3. It also works with stream processors like Spark Streaming, Flink, Storm, and others. So just to kind of summarize this talk, I think operational analytic databases, I think they're very useful in the NetFlow world. I think they're very helpful for being able not just to do analytic queries and not just to do search and filter queries, but to really be able to do different types of search and investigation as well as reporting and monitoring. And as I mentioned, Druid is a project that's incubating the Apache Software Foundation. It's a community-run project. There's about 10 or so different companies that are actively contributing to it. We have a community webpage that you can go to and you can download it. And then there's also sort of an enterprise-y version that we host on Imply as well. So with that, that's my talk. And I'm happy to answer a couple of questions if anyone has any at this time.
Hi, Igor Gashinsky, Yahoo/Health. We use a lot of Druid in a bunch of our operational analysis engines. One thing that I kind of uncertain about is the use of Druid for Flow. The way that I see it is that Flow has a couple of use cases. Flow could be real instantaneous. I need super high fidelity of data, what happened in the last 5 minutes, and I need super high fidelity. Doing any sort of rollups that you're suggesting will completely make that go away. Then there's what you're suggesting, which is roll up to 5 minutes. I probably want to keep that for about a month. But a month ago, every 5 minutes roll-ups are kind of irrelevant. So like, how do you see this architecture where you almost have 3 different tiers of data that needs to be available, all as a fast set search, which is ultra high fidelity, high resolution, last hour or so to help operational troubleshooting, break fix, like very high level of data, and then what happened over the last 5 years showed me a trend which also has to be aggregated probably by interface, by property, by customer type, tons of different dimensions. And if you're doing aggregation that does approximation, which I'm not quite sure what you meant by that, but if by approximation you mean loss of accurate data of this was customer A versus customer B, that might be an issue. Like, how do you deal with that?
Yeah, so the very short answer is actually in Druid today, all the rollup, all the approximation is optional. So you can actually disable rollup and just maintain your raw data. So one very common model that I see is people don't roll up raw data for a very recent span of time, whether that's the recent hour or the most recent day. They basically just keep the raw data around. And then because historical data is also important and it gets prohibitively expensive to store flow data for up to like 2 years, then there's different levels of rollups that start getting applied across a timeline. So for example, you might keep the most recent day of the raw data and the most recent month rolled up to 5 minutes, and then everything older than that rolled up to like an hourly granularity. Because as data gets aged out, I've just seen most people don't need to query like what happened at a precise millisecond in time. It's actually more about broader trends within the data. So that is something that Druid does support today, and it's very common now for people not to roll up data. The second part of that answer is we believe in a lot of like disassembled architecture, so pulling raw data from like a message bus such as Kafka. So for both Kafka and Kinesis, we actually are providing very strict guarantees on data loss. So we actually guarantee no loss of data, no duplication of data. So we're guaranteeing exactly once consumption semantics. And that's with the overall idea that your whatever queries you issue are going to be 100% accurate. So all the approximation can be turned off. There's obviously going to be performance and storage trade-offs there, but if fidelity of your data is important, then that is something that's being strongly supported today.
So what would the performance implications be if you turn off all those rollups?
It really depends on what your data looks like. So with some data sets, people get like a 2-to-1 rollup, which means that data stored in Druid is about half the size of the raw data volume. Some people get 1,000-to-1 rollups, where the data stored in Druid is 1,000 times less than the raw data, and it really depends on the number of attributes and then the number of unique values within those attributes. If you have, as a number of dimensions starts increasing, as it does with flow data, it might be not that impactful, but it really varies from data set to data set, and it's just a trade-off that the operator has to make. How much do you want to spend on storage? How much do you want to spend for better performance versus what kind of fidelity of the data do we want to ensure?
So are you almost suggesting that there's two different operational databases, one that's designed for the last hour and another one that just does constant rollups?
What I would say is it's not like two types of database, but it's actually a more sophisticated data model. So within a system like Druid, it would be kind of one data set, but part of that data set is the raw data, part of that data set is a more rolled up data, and maybe part of that data set is an aggressively rolled up data where certain attributes are even stripped from the data to get better roll up. So I guess it would be in a single table. There's not a uniformity of how things are compressed and stored within a single table. You actually have homogeneity, but that's what's ultimately, I think, going to fit best with the use case while maintaining fidelity.
So, I mean, that's kind of my question is, I know you're a contributor to Druid, so thank you very much.
Yeah.
We love using that. But you're comparing it to other things. Do you feel that some systems are better than others at doing?
Well, I think this roll-up problem is not something that really any system has solved. I think the homogeneity in the roll-up is actually, roll-up is a concept that's native to Druid that doesn't really even exist in a lot of other systems. If you were to use the ELK stack, for example, you don't have this option even to compress your data. You're basically just storing the raw data as is. So you can always just do that in Druid, but I think Druid adds that additional level of sophistication to be able to start pre-aggregating some of your data if you need it for your use case. Thank you.
Hi, Dave Siegel, Siegel Group. Could you provide an example of what this approximated value looks like? You gave the example of the device ID. What does that look like? How is that approximation doing, and what kind of data is being lost in the process?
Yeah, so there's a range of approximation algorithms. They're also called sketch algorithms, and some of them they're really around set analysis. So you imagine you have a set of elements, and one of the queries that you want to do is count the number of unique items within a set. So if you have a dimension that's device ID, and if you start having millions or billions of unique device IDs, most of the time you don't care about every single unique device. What you care about is the number of unique devices that you have at any given point in time. And this is something common with user ID as well. So if you have a user ID or a session ID, you don't really care about every unique session. What you care about is the number of unique sessions that you have. So this is the type of workflow that can be calculated approximately. This uses an approximation algorithm called hyperlog-log. And the idea is that as opposed to storing every single unique user ID and then counting all of them, you store it in a probabilistic mathematical data structure, which gives you about 98th percentile accuracy. But if you can start approximating some queries, you can get significantly better performance on those queries while significantly reducing storage as well. So if you have 1 billion unique users, maybe your approximate query gives you 999 million, but that's enough to understand kind of the trend, and that query can be done 10 to 100 times faster than if you stored every single user ID and counted all of them. Does that make sense?
Kind of. I guess I'd have to play with it, see what it's actually
Yeah,
it sounds like it would make the column mostly useless for a lot of different variables that have a lot of uniqueness.
It depends. So the trade-off is that you lose information about, using user ID as an example, you would lose information about every single unique user ID. But that's okay if all you're trying to do is count the number of unique users. If you actually care about the unique session IDs or user IDs and you have to maintain them, then approximation is not going to work. But if all you care about is counting the number of unique sessions and unique users, then approximation is something that can be potentially considered.
Okay. My other question related to scalability, if you were to try and put this into a large network at scale,
yeah.
Does the hardware and those search times, do they do they scale in a linear way, or do they get more challenging? Do you get any optimizations as you get into the trillions of rows in the database and networks that are ingesting terabits per second values?
So with most distributed systems, when a system like Druid, which I talked about, they're designed to be horizontally scalable. So the idea is that performance, ingestion rates, and also query performance are going to be consistent even as your data scales. So as you go into petabytes of data, your query performance is actually, like if you're targeting for sub-second query performance at gigabytes and you go to petabytes, you should still be able to maintain that sub-second query performance by adding new hardware to the cluster.
So it doesn't break at some point when it just stops, you can't grow it anymore?
There hasn't been a cluster out there that's kind of pushed the limits. All systems I think have an upper limit, but I think of all real world data sets that we've ever seen, we've never seen that limit yet.
So what would you say the biggest system is that you've tested it with?
I used to work on a Druid cluster that was a few hundred petabytes of data, and then the data compressed down to about a few hundred terabytes across a few hundred nodes. I know of some systems out there that are about a few thousand nodes today, and these are some of the largest data sets in the world, some of the largest networking data sets in the world as well. So at that scale, still seems to be okay.
All right, thanks.
Thank you.
Paolo Lucente, NTT Communications. I don't have a question. Actually, I have a comment which is linked with the previous questions or comments. So although I'm not contributing to Druid myself, I'm a big supporter of Druid. In NTT Communications, we are using Druid for a variety of different use cases, ranging from flow collection to collecting BGP, SNMP, streaming telemetry, and things like that. And so, for example, there was this whole focus on the roll-up versus not roll-up and things like that, right? So, for example, I use flow collection mainly for business intelligence purposes, and in that case, it's a lot of data, and I use roll-ups because, for example, if a specific flow was at whatever megabits per second at 5 minutes before or after, I don't really care because it's not forensics, it's business intelligence. But for example, I have other data sets where I am collecting BGP or streaming telemetry, and there I really don't want to miss on any single point of data, and for example, the roll-ups are disabled, right? So I wanted just to clarify that, make that comment, and congratulate Fanjin for a great product.
Thanks, Paolo. Yeah, so much appreciated. There's folk from Yahoo that presented, and Paolo spoke about some of his use cases. Druid is pretty widely adopted out there. There's a lot of public use cases online, public use cases about different companies at different scales. So encourage everyone, if they're interested, to check that out. If there's no other questions, I want to thank everyone again for their time.
All right, before everyone takes off for lunch, which is on your own today, we have the Tuesday survey winners. So if they're present, they win. If they're not, we'll go to the next name. So, Henry Clay Dean, are you in the room? Yay, awesome, first time, easy. That is a subtle reminder as well to take your surveys for today. They will be doing a drawing this afternoon for the Wednesday's survey. So, there you are. All right, again, lunch is on your own, and then we'll be back here just after 1, so enjoy your lunch.
So before the program committee starts up with our speakers, we're going to ask the election committee to come up and share the announcement of the results.
Sorry, thank you. Okay, all right. So we just want to thank all of our candidates for participating and all of the members who voted. Really appreciate it. So now to the results. Don't leave it waiting. Okay, so our election results, we have our board candidates, Susan Forney and David Segal. What? Siegel. David Siegel. Sorry, David. We had a pretty close race, and we had 93% approval for our amendment updates, or our bylaw amendment updates. So thank you all for that. And all of this information is going to be available on the NANOG website going forward, so feel free to check it out. That's everything. Thank you, everyone, for your time. And that's the end of the results.
So we'll get started here. Our first speaker, before he comes up, I want to remind everyone, please fill out the survey. There's still a drawing at the end of the day for another, it's the Apple Watch, I think. So please fill out the survey. PC really values that feedback. And I'll remind you again and again of that. So our first speaker here is Faisal Iqbal. He's going to talk about data plane monitoring and segment routing networks.
Hey guys, so I'm Faisal Iqbal. I'm a software engineer for Cisco Systems, and I'm going to talk about data plane monitoring and segment routing networks. Unfortunately, Clay can't join me, so you'll have to live with me. So data plane monitoring, of course, is very near and dear to most of the operators. You want to make sure your network is functioning correctly, everything is going the way it should. There are no traffic black holes or other faults happening in the network. So for most of the slides, I'll just use this topology over here. So it's pretty simple. I'll be describing it. Don't need to basically memorize it. So black holes occur when a router starts dropping traffic. And it could be that we are dropping, it could be for a single prefix, it could be just over a particular link, or it could be all the traffic over the network. And there are multiple reasons that it could occur. Sometimes there's a forwarding inconsistency where one of the network, let's say one of the line cards is a bit behind, it doesn't have the latest update. Sometimes the control planes of the two devices can get out of sync. And user can also, of course, can make a mistake, misconfigure, and that could lead to a black hole. So there are various causes. It's a significant pain point and something that we want to address in any decent OEM solution. So I'll just highlight this using a very simple example. So here we have a VPN, which C device C1, which wants to send traffic towards CE2 over the MPLS network. So in this case, it will send the packet to node 1. So node 1 will slap the transport label and the VPN label, and then send the packet towards next hop. So if you notice over here, the label, MPLS label that is being sent, it is unlabeled on the next hop. So, and this is not a very uncommon scenario in the network encounter. So in this case, it may just pop that label and just expose the VPN label prematurely and send it towards the next hop. And because, of course, the next hop is a core node, it does not understand the VPN label or the payload underneath it, so it's going to drop the traffic. And in MPLS networks, typically, it could also happen that you have ECMP in the network, and in this case, you may send the packet towards incorrect node, and that will lead to a black hole as well. With segment routing, the labels are global, which means that most of the network devices understand the labels. So even if the traffic is not sent to the correct node, it may still end up reaching the destination, but not to the expected path. It may take a path that is probably longer, or maybe introduce congestion in the network, or it may even break SLAs. So this is what I'm using as path divergence. So again, I'm going to highlight it using an example over here. So here, let's say we have a policy where we want to send the traffic from node 1 to node 7 through node 5. So in this case, we can have an MPLS label stack where the first label, 16,005, is the label to reach node 5. And then the next one is labeled to reach node 7. So node 1 builds this packet, send it toward the next hop, 3. So 3 is a penultimate hop. So it's supposed to pop the label and then send the traffic towards 5. But let's say there was an issue in 3. So instead of popping the label and sending it towards node 5, it instead sent it towards node 6. And because the packets still have 16,007, node 6 will pop the label, it understands it, and send it towards 7. So now the packet did reach the destination, but it is not taking the path that we expected it to take. And that can lead to congestion and other issues I mentioned above. So currently, there are various fault detection mechanisms available for operators. Broadly, we can categorize them as proactive, which means they are constantly scanning the network and making sure everything is working the way it should. But for large network, that gets really complicated because it's tough to proactively monitor the entire network very easily. So then operators have to also rely on reactive tools as well. So in reactive, you get alerted by a fault, and then you use your arsenal of OEM tools to identify the fault and the point of failure so you can take a corrective action against it. And then we can also say that the tools available to you right now, they could be local, which means that they just rely on the node. They don't send any probes or anything outside the box. So for example, some routers and switches have a label or route consistency checkers, which make sure that label or routing database is in sync with FIB. But on the other hand, we have LSP ping or BFD. And these tools validate the entire LSP. So if something is broken, BFD can monitor it proactively at a very fast rate. And LSP ping it's not meant to be constant, very fast rate, but it can detect more faults and various other use cases as well. But overall, we can say that in this case, these tools are incomplete because they only identify a subset of faults. For example, BFD, LSP ping, they cannot detect path divergence because packets still reach the destination. So it will report everything is OK. And then there are also scalability challenges with it because you have high number of ECMP and ECMP combinations. So it just gets into an ECMP explosion. It's nearly impossible to monitor every single path end to end. So we think that we need a tool that can complement the existing tool set that can, well, we're not going to go away from end-to-end monitoring or local tools, but we can come up with something that complements them to monitor more fast that can remain otherwise undetected. And for this purpose, we are introducing segment routing data plane monitoring. So SRDPM is an independent solution that allows a node to test its entire forwarding path end-to-end in the sense that ingress to egress on the same device, not end-to-end in the network sense. For any MPLS traffic that could be received from any upstream towards any downstream ECMP. So in this case, we are not testing just one path. We're not just testing local probe and sending it out. We try to model the customer traffic exactly. And we do this through a distributed and localized detection mechanism that is based on source routing paradigm. So in this case, it can monitor the entire network. It can monitor the network proactively, constantly going on in the background, detecting any faults. And it's localized because we don't go beyond one hop. Each node just checks itself and then its immediate neighbors. It doesn't try to go beyond that because then we'll run into the same issues that we have with end-to-end tools. Instead, we can distribute the detection mechanism, detection over work to different devices in the network. So each device can just check itself and its neighbors, and you don't have to rely on just a single tool or one end-to-end mechanism. And because underneath, we use a specially crafted LSP ping packet. So LSP ping is widely supported by most vendors at MPLS level, and most operators probably who deploy MPLS, they use it every day. So you don't have to go to IETF, write a draft, standardize it, and hope that all your other vendors also support it. It's interoperable by design. And because we are relying on source routing, so in this case, source routing has adjacency set, which means that we can pin down exact interface or a link. So in this case, we can pin down the upstreams and downstreams, and using this, we can make sure that we test each upstream and downstream combination. Because you could have multiple line cards, and maybe if you test just one of them, it doesn't mean that the other line cards are functioning the way it should. So now I'll go into the mechanics of data plane monitoring, where I'll highlight what exactly, how it works. So broadly, it's a two-stage process, or how we call phases. So first, before the real work we want to do is we want to make sure that we are forwarding every prefix that can get from upstream towards the correct downstream node. But before doing that, we want to make sure that all our links are forwarding traffic correctly. It's not that let's say if one of the links is broken, then we'll see the same breakage across all prefixes, and we may think that it's an issue with the prefix when it's really a link issue. So we address it using adjacency validation. And once we have that one, then we'll also use it as a building block for our prefix validation phase. So here, adjacency validation, the basically idea is that you want to make sure that you are able to send and receive traffic correctly to each one of your neighbors. So here, let's assume that we have this topology again. So we are working on node 3. That is the only node that is running DPM. No other device in the network is running DPM right now. So in this case, it has links to neighbors 1, 2, 5, and 6. And right now, I'm showing only single links, but of course, you could have ECMP there as well on these nodes. So for each neighboring link, node 3 will construct an echo request packet that goes to the neighbor and then comes back on the same link. It will just transit through the neighbor. It will not get punted on the box. The box doesn't need to do any, the neighboring box doesn't need to do any software processing there. It will just simply switch the packet back to you. And then once we receive the packet, we can validate if we were the intent target. So in this case, for example, we have adjacency set label, first one, 24031, to take it from node 3 to 1. And then 24013 will bring it back from 1 to 3. So if we receive the packet back, because packet will have enough information coordinate, we'll know that we are the intent target and we received it on the correct link. Let's say if packet end up on node 4, then we'll receive a fault. This link is not functioning correctly. And we can do this for the remaining links as well. So we did it for node 1. Now we can do the same thing for node 5 using its own adjacency set labels to and from, for node 6, and then node 2. So once we have that one, in this case, we know that all our links are functioning correctly. And again, I'm going to iterate that there's no software processing involved in the neighboring device. They're just going to switch the packet back to the DUT, in this case, node 3. Node 3 is the only one which is sending and receiving probes. So once we have that one, then we can identify if there's any malfunctioning link. So malfunction could be that maybe the link is dropping traffic. It could be that it is forwarding the traffic either like the DUT or the neighboring device. It is sending it towards incorrect link or incorrect device entirely. So we can't use, if there's any malfunction, we can't use that particular link. We'll have to exclude it from our further validations. And also, we use this as a building block for the next phase, as you'll see. So prefix validation is what we really are interested in. We want to make sure that we are able to send and receive traffic from any upstream towards any of our downstream neighbor for that prefix head, and we want to do it for every prefix head in the network. And we achieve it by looping the traffic because we want to simulate customer traffic path. We don't want to just generate a probe locally from RP, send it out over line card, because then customer traffic doesn't take that path. Customer traffic comes on an ingress line card and then goes out via the egress line card. And we want to model that customer traffic path. So we do this by looping the traffic using the adjacency seed label we just discussed. And then using this looping, we can actually get the packet back on the device. And then we have a prefixed label. Once we receive the packet, the next label will be prefixed label, which will take it towards one of the downstream devices. So now for any, let's say like we have a DUT3, we can identify the upstream link and the downstream link for any prefixed. And if one of them is malfunctioning, we can exclude it. So in this case, for any prefixed, we'll go through this process. So here we have, for each upstream and downstream combination, the DUT, in this case, the device under test, node 3, it will build a packet, and plus echo request packet, because that's what we use for this one. That will go to our upstream neighbor, comes back to us, and then expires at an immediate downstream neighbor. And we can set the TTL to 3 to make sure. That way, the packet doesn't go beyond one hop. We just go one hop up and then one hop down. And that way, we are just limited in this one. We don't have to worry about the scalability challenges of end-to-end mechanisms. And then we have the prefixed label, because when the packet comes back at the DUT node 3, it will only have prefixed label. The adjacency labels would have been popped. So in a way, customer traffic as well will have the same label. So we are forwarding exactly like any customer traffic would. And because we could have multiple ECMP, here we have 2 ECMPs. So we want to make sure that we can test each one of them separately. So LSP ping has 127/8 destination addresses, and we can play around with the entropy to make sure that we can test each one of them correctly. And once we send it out to the correct downstream, we want to make sure that it reaches there. Let's say like if hardware and software are out of sync, we thought we were sending it towards node 5, but it ends up at node 6, we can't detect that scenario. So we include enough information in the echo request packet that we can do that. So we include the ID of the destination that we are trying to reach, and then the information about the label stack that should be expected at the next hop, the interface on which the next hop should receive the packet, and of course the next hop ID. So we send this packet out, it reaches the downstream device, and then downstream can make sure that it has a labeled path to reach the destination. Here our destination is 7. So node 5 can make sure that it has a path to reach the destination 7, and that path is labeled. And then it can also make sure that it was the intended destination. We didn't mean to send a packet to node 6, and it somehow ended up at node 5, and it was received on the correct link. And this information, along with the information of the next hop from node 5, is sent back towards 3 in an echo reply. So this is standard echo reply here. Node 3 is not running DPM. It's not even DPM aware. From its perspective, it just received an echo request packet, and it is just replying to that echo request. So it could be a non-Cisco box. It could be running an older version. That's the beauty of it. It's interoperable by design. So once we receive the reply, we can make sure, okay, if there was any fault, then we can alert the operator that for this particular combination, we are seeing an issue you may want to monitor. And we can also, I'll talk about remediation as well. That's also possible. And then we can go on to test the remaining combinations. So here for the same downstream 5, the traffic could potentially come from the other upstream as well. And similarly, we can test it for the downstream 6, both combinations, and then for remaining prefixes as well. So that way, we can test each upstream and downstream combination for any prefix in the network. Right now, I've just described it for node 7. OK, so as we saw, we are not going beyond one hop. So in this case, each node just takes the packet to upstream and then downstream, not beyond that one. So it will detect any forwarding, because we are exercising entire forwarding chain at the DUT. So if there's any forwarding issue for a particular prefix head, we will detect that prefix that will detect that issue regardless of upstream or downstream neighbor that we have. And it can also detect most forwarding issues at our neighbors, at our downstream neighbors. For example, if downstream does not recognize that prefixed label, or it doesn't have a path onward. So it receives the packet with label, but it cannot send further with the label. It cannot send it unlabeled. We can detect that kind of scenarios as well. But if there's anything beyond 1 hop, so in this case, 7 or 8 or 4, they are not our immediate neighbors. So of course, we are not sending any probe to them, so we will not detect faults there. But DPM is meant to be deployed throughout. It's a distributed detection mechanism. So instead of deploying on a single node and trying to test entire network, instead you can offload the work to different devices. So you can deploy DPM at strategic nodes in the network to make sure you have a good coverage in the network. And of course, you want to make sure that operator gets a really good fault. It can operator get a fault notification message, and that notification message is informative and accurate. So when DPM detects a fault, it will alert operator. It could be through a message on the box, or it could be through telemetry mechanism. But it will notify it, and that notification will contain the information of the fault. It will include the links that are involved, the prefixed label, as well as a brief error description of what really went wrong. So you can take, and we can also have a remediation action, because once we know all this information, we have effectively isolated the fault in the device. We know what's going wrong with which prefix, what are the nodes, and what are the links involved in this one. And then based on the error description, we can know that, okay, what particular message, maybe it's an unlabeled packet. Maybe in this case, the next hop is not being sent correctly. Maybe one of the devices is running slow. So we can take a remediation action. Let's say reroute the traffic, or reinstall the forwarding entry, etc. And then we will try to avoid fault as well. Okay, so far I have discussed this mechanism as a proactive, where it is constantly running in the background and then detecting faults. But we want to be flexible. We know that some operators, maybe they're running their own probes at a very high rate, and they don't want to run DPM very, very fast rate. Instead, they want to run it slowly over, but then based on certain network events, maybe they want to just test a particular prefix is installed correctly across all the line cards, across all the links. So you can test a single prefix, or you can test all prefixes. Or maybe you want to do it based on a certain network event, because typically faults don't occur in steady states. Maybe a link went down, some new link or device got added, so now you have forwarding updates, your IGP converged. It's going to install a bunch of forwarding updates on the control plane to hardware path. And that's where, in this, when you're doing this installation, when you're installing these forwarding updates, that's where you can potentially cause issues, where it is gonna, if there's any bug, or maybe one of the line cards is slow, so it didn't get the updates, it's running stale version. Then when you have these kind of triggers, in this case, it could be a link going down, or an alert from IGP that it's converged, there's no further update for, let's say, a certain amount of time. Then you can run DPM to make sure that all the forwarding entries are installed correctly. Or it could even be a controller-driven trick. So we can let operator know that, okay, whenever they send a particular trigger, then we can monitor a set of, or all the prefixes in the network. Oh, my bad. So in conclusion, we believe that DPM is an innovative solution to data inconsistency and identify any traffic black holes in the network. Instead of trying to do end-to-end fault detection or try to test all the possible combinations, instead we distribute the detection work through the devices in the network, where each node just tests itself and its immediate neighbors. And because we are using LSP ping, so it's interoperable by design. There's no standardization required. Your neighbors doesn't have to be running a particular version of the software or a particular vendor, etc. As long as they are able to send and receive echo replies and echo requests, they should be able to work. And we are not planning to, as I mentioned earlier, we're not intended to replace existing tool set that you have in your arsenal. They have their own place. They're really suitable. We are not trying to be BFD. We're not trying to be LSP ping or discovering all the possible paths in the network, et cetera. Instead, we believe this tool complements the existing solutions that operators may have, and then instead of replacing them. And of course, it is ready for adoption by customers. We are working very closely with some of the customers. So in this case, Bell has joined us as the co-author of this talk. And if you have any question, I'll be very happy to answer these questions. I guess that's it.
Andrei Kostin, Tixavi. Have you done any scalability testing for this solution?
Yeah, of course. So scalability is very important. The thing is, you could have some networks maybe running few hundred or even less than 100. Other could be running thousands of prefixes. So yes, scalability is an important concern, and we have various tuning parameters because in the end, we want the solution to be flexible. So in this case, you may want to have a solution where you can tune the detection interval, you can tune the packets per second that we are sending with. So using these tuning parameters, we plan to cover up to several thousand of prefixes. We can discuss separately, but I can give you the numbers on that one. And of course, for each one of them, we can have a high number of ECMP as well, upstream as well as downstream.
Okay, thank you.
Okay, I guess you guys have 5 minutes before the next one. So, all right, thanks, guys.
Thank you. Thank you, Faisal. I'm going to introduce our next speakers. We have 2 of them, Ian Flint and Varun Varma, come on up. They're going to talk about Panoptix, which is a network telemetry platform.
Hi there. My name's Ian Flint. This is Varun Varma, and we work at Oath, a company formerly known as Yahoo and AOL and Edgecast. So we were all combined as part of the acquisition of Yahoo by Verizon. And I run network automation. One of the big challenges that I faced when I came onto the team was the proliferation of point solutions for doing monitoring of devices. And so we had a whole bunch of them. We have a significant MRTG footprint that's hitting our devices. We have a custom SNMP poller called YWatch that's hitting our devices. We have a point solution around load balancers, just all of these systems that had grown up organically over the years. And the systems that depended on them that had also grown up around them. And so one of the challenges that we undertook to solve was to take those and consolidate them into a single polling platform, a universal polling and metrics distribution platform, which we called Panoptix. That's what we're going to be talking about today. So,
hi, my name is Varun. I'm the lead engineer for Panoptix. And as Ian had mentioned, so essentially we built Panoptix as a Python-based network telemetry platform. There are 3 distinct components that Panoptix has. There's discovery, polling, and enrichment. And we'll be talking about some of these details during this talk. Here is an overview architecture diagram of what Panoptix looks like. So it's based on some supporting services. There is Celery, which is a very popular Python distributed job management system. There's Redis, which is an extremely fast in-memory key value data store. There's Zookeeper that provides distributed locking and leader election services like that. And then, of course, there's Kafka, which we use as a message bus. On top of all of this, we actually built a plugin framework, and I'm going into some of the details later. Now, we implement 3 types of plugins, discovery, polling, enrichment. And then on top of this entire framework, or the stack, we implement device-specific plugins. Currently, we have plugins that use SNMP and APIs to actually collect telemetry data.
There's a bunch of supporting services in addition to the core platform, because obviously after we collect this entire data, we have to store this and analyze it. So we have a time series database that we use. We have an internal CMDB that we use for device discovery. And then we use Chef for deployment and configuration. I'm going to go through some of the core concepts that Panoptix as a platform has. So the very first concept is this notion of plugins. And this is where Panoptix is actually fundamentally different from a lot of SNMP-based polling solutions. So what a plugin is essentially an implementation of a well-defined Python interface class. So you can essentially, because it's Python code, you can actually write code to collect from any source that you like. It could be SNMP, could be API, CLI, or anything else that might come up in the future. As I'd mentioned, there are 3 types of plugins: discovery, enrichment, and metric plugins. Another core concept in Panoptix is this notion of resources. So what a resource is it's essentially an abstraction of what should be monitored. In the most common case, a device or a network device or a host is a resource. But a resource could be an external API endpoint. There's metadata associated with resources. Another interesting thing in Panoptix is that we've come up with a DSL, which actually mirrors or is quite close to SQL, which lets you actually select resources. You can see an example of the DSL on the screen, where we're saying, okay, I want you to apply certain type of polling only to devices which match this criteria. Now, typically, these types of DSLs are available within time series databases on analytic tools. But here, the difference is that we actually have made it available even at the time of deciding what to poll and how to poll it. Another concept is metrics, which obviously is one of the core things. A metric is anything that can be measured. So it's essentially always a number. Metrics typically tend to be fast changing. And while that might sound obvious, I'm going to contrast it with something called enrichments later on. And like I said, because of the plugin architecture, metrics can actually be collected through any mechanism. Okay? Another concept that we have introduced is the notion of enrichments. Now, what enrichments are things that are not numbers. They could be numbers, but essentially these are things which are not that frequently changing. A perfect example would be when we're collecting telemetry data for interface metrics, right? So the interface counters are metrics, but the interface name is actually an enrichment that we apply. And the thing is, and enrichments might not necessarily just come from the device that's being monitored. It might come from external systems. One example is when we poll a device for, say, BGP sessions, we get back ASN numbers. Now, we might be interested in reporting the actual peer name, not just the ASN number. And that's where, that's not something we can query from the device itself. So that's, again, a place where the enrichment framework comes in, where we can query and enhance the data that we've collected from the device by using external lookups. Also, because metrics are typically not numbers, they're typically strings, they tend to be more expensive to process than metrics. And that's one of the reasons there's transformation and lookups needed. Case in point, for example, I mentioned the ASN number to name lookup. It's not something you want to do on every poll cycle. It's also something that, because they're expensive, we tend to cache them. Again, an example is interface names, interface aliases, things like this, which we don't actually need to collect in every poll cycle. Overall, what this does is, by being able to divide metrics and enrichments, is it actually lets us scale a lot, because we don't have to collect the complete set of data on every poll cycle. Now, a word about the data encoding and distribution. Panoptix was built from day one as a distributed system. We knew that at our scale, building a system which could only scale vertically, which means we had to add more processors or more memory to the same host, would simply not work. So we've actually built it as a horizontally scalable system. And there are two dimensions to that. One is the fact that the three subsystems that I mentioned, discovery, enrichment, and polling, are completely decoupled, which means we can scale them out individually. It also means that within each of these systems, we can actually spin up more hosts. And for example, if I need more polling capacity, I can simply spin up more hosts, and it becomes part of a cluster, and I get more polling capacity. Because these systems are, because it's a distributed system, we obviously need a way to pass data between them. We use Kafka and Redis, depending on different use cases, to actually pass data between these subsystems. The other thing is, again, because we're passing data, we need to choose a serialization format. So we decided to go with JSON. Now, JSON is extremely inefficient and it's slow, but then it is actually very operator and developer friendly. So it's a cost we were willing to pay. This is what the overall workflow for this looks like. So, obviously it begins by us collecting data. There is some post-processing support that we have. We call these transformations. An example of a transformation is that when we collect raw counters from a device, sometimes it's not meaningful to send it as is downstream, so we can actually convert them into gauges. And then once we do the post-processing, we place the data on the message bus, and then we have different consumers. Here are two workflows that I've shown. There's one workflow that takes the data and puts it in a time series database, which we actually use for graphing, alerting, and our internal time series database actually also stores the data on our internal grid, which we use for analytics and reporting. At the same time, there are use cases where we need the most recent data, not necessarily the historical data. So we actually have a consumer which stores this data in MySQL and exposes this through an API. And then we built UIs and CLIs based on top of those APIs, and I'll be showing an example of what that looks like. So given that we serve 1 billion plus customers, obviously we have a very large footprint. And there are a lot of things that we learned while operating this. First, let's talk about what the scale we're operating at is. Now, this is an indication of orders of magnitude. These are not absolute numbers. So we have hundreds of thousands of servers. We have tens of thousands of network devices. We have millions of time series. We do collect data every 60 seconds, which is actually faster than typically what we were doing with MRTG of every 5 minutes. Now, some of the scaling issues we faced. I mentioned earlier that Panoptix was designed to be horizontally scalable, and this was intentional. We paid a lot of upfront development cost to do this because, frankly, this is not easy to bolt on. Scalability is not a feature. It's a design principle, so you kind of have to take care of it while designing the system. We decided to go with Python. It is extremely slow, extremely inefficient, something we were prepared for, and it turned out to be true. What we have done is there are some high throughput actions, like specifically the actual SNMP protocol interactions, which we've delegated to C extension modules so that we can actually get performance. And then again, at our scale, we broke everything. All the default installs for Redis, Zookeeper, Kafka, they would just fall over because we would hit all the default limits. So there's a lot of tuning we had to do for each of these systems. The other aspect for scaling was with data this large, we did not want to build a centralized system, both for performance and availability reasons. So the way we did this instead was that we have these local deployments in each of our data centers. And what we do is these data centers collect data for their, obviously, all the network devices within the data center, but also collect devices for nearby regional sites. At the same time, we don't want discovery of data to be problematic. So somebody using an API should not have to figure out where they can get this data. So what we did was we came up with a federated API structure where what we do is between all these data centers, we actually cross-populate the metadata. So each data center does not have all the data, but it knows where to get all the data. So you can make a query and say, okay, I'm interested in data about device X. And you might get a response saying, here's the data. Or you might get a response saying, okay, I don't have the data, but I know who does, so why don't you go ask that person? And this design has helped us both with scalability and fault tolerance. The plugins that we have already written, we have support for Arista, Cisco Juniper metrics, we have system metrics, we have something we called functional metrics, which is go beyond just the CPU memory, and they're very, very device and platform specific, and more importantly, they're usage specific. So if you're using an A10 load balancer for load balancing, we have different functional metrics versus when we use it for large-scale NATs. What we've also done is, because this is a platform for telemetry collection, we've actually also built state and topology collection for Cisco devices. This is something we're looking at actually integrating back into our discovery so that we don't only figure out what devices to monitor through our CMDB, but through an actual walk of the network. Some operational experiences that we've had, and anybody who's worked with network telemetry, I'm sure would have seen these. We had a lot of inconsistencies between metrics which were reported from different platforms and different OS versions of the same platform. And frankly, in terms of development, this was our single biggest time drain. SNMP, it is really old. I believe the SNMP v2 specification came out 21 years ago. So it is old, but it is ubiquitous. As much as we'd like to be able to use API and streaming telemetry, there just simply are many cases where a lot of telemetry data is not exposed through those. So it's something we have to live with. API performance tends to be much better than SNMP. Again, anybody who's done telemetry would know this. The other thing is, when we were building this, we had some use cases. Like Ian had mentioned that there was a whole class of services or systems that we had, and we knew what we wanted to replace. But we also knew we didn't know how this data would be used. And that's where, for example, using Kafka proved to be the right choice. We already have 3 types of downstream consumers which transform the data and send it to different systems. And this is a much better approach than trying to collect data, the same data in different ways so different downstream systems can consume it. I'm sorry, I think the slide's been repeated. Oh, sorry, I'm going back. One interesting thing is, one thing we were very careful about is, even though we place all our data on Kafka, we do not integrate those raw streams with third-party systems. Now, this might sound counterintuitive because one of the big advantages of using Kafka is there are so many consumers that you should be able to hook in any consumer and get the data. But here's the problem. If you do that, you can never upgrade. Because the problem you will have is you'll be tied into a certain Kafka version because there's a downstream consumer that depends on that Kafka version, or you will be tied into a specific serialization format, whatever you were exposing on sending or serializing with on Kafka. If you ever change that, your downstream consumers will break. What we do instead is that we actually take this data and we store it in a transient MySQL database and expose APIs. And I'm going to show an example of the APIs we have. And the advantage that has is it completely decouples my system. We can change the internal serialization. Heck, we can even get rid of Kafka for something else that comes along without our external contracts changing. We built custom UIs. Again, I'll show a couple of examples of what that looks like. These are examples of APIs that we have. On the left, you would see this is a very purpose-specific API that we've built to get data for whips from load balancers. At the same time, and this tends to be very easy to use and performant. We also only expose the last data point through the API. We also have a API which actually exposes historical data, and you can do ad hoc queries on it. This is actually an OpenTSTB API. So this is not something we've built. Internally, we use OpenTSTB. Tends to be slower, but then you can run aggregations and you can get historical data. One of the things I mentioned in the architecture slide is that we have a time series database. So we actually have an in-house time series database and visualization solutions, which Ian actually had architected. It's based on OpenTSTB with a lot of, obviously, performance optimizations, a lot of other improvements. This is an example of a dashboard that we've built based on our internal TSTB and the internal UI that we have. Now, because it's a centralized TSTB, our team doesn't have to manage it. It's managed by a central team for the whole of Oath, and there's economies of scale and operations are simpler. Here's an example of a couple of custom UIs that we've built. The left-hand side is actually a device dashboard. The right-hand side is actually a WIP dashboard. Now, these have been built using the purpose-specific APIs that I had shown. And because they only expose the last point-in-time data, they tend to be performant, so our UIs are actually quite responsive. Looking forward, one of the next things that we want to work on is actually streaming telemetry. We have a framework in mind where we use a streaming telemetry collection. GNMI is the leading contender. But we also reuse the infrastructure that as we have. For example, in the GNMI case, we do need to create outbound connections to actually get streaming telemetry from them. And for that, you need an authoritative source of devices or resources to connect to. That's something Panoptix has. Similarly, for GNMI, you would want to, the raw metrics or telemetry data that you get over streaming, you will again want to enrich them. Examples of enrichment, I gave the ASN example, but there's another example. For example, the geolocation, the physical geolocation of the device is not necessarily something that you can figure out from the device itself. So these are external enrichments that we can apply to the raw metrics that we collect. Now, we've actually spoken and presented a lot of this at NANOG 70. So the big thing, though, is the stuff that we've done after that. When we presented it at NANOG 70, we had discovery and polling. We did not have enrichment. What that meant was that on every poll cycle, we would actually be getting all the static information again, which had scalability problems both for the platform as well as for the network devices. By adding an enrichment subsystem, we have alleviated those concerns. We have implemented we actually have implemented a whole bunch of plugins to give us full coverage or close to full coverage with a network which is a multi-generational, multi-vendor network like ours. We worked out scaling issues. Obviously, that required a lot of platform changes and tuning and things like that. But most importantly, what we wanted to talk to you about is that today we are actually announcing the open sourcing of Panoptix. We are releasing an MVP. We're open sourcing the core platform that includes the 3 subsystems that I've been talking about. We are open sourcing interface metrics and enrichment plugins. This is a very small subset of the plugins we have, but in the spirit of releasing an MVP, this is what we'll be going to market with. And we're also introducing an integration with InfluxDB as a time series database. So this is an example of an InfluxDB dashboard that you can create if you actually use the open source time series, the open source implementation that Panoptix has. And you can actually go get it at this URL. Any questions?
Hi, Tony Tauber, Comcast. It looks like very good stuff, and set up the way I would think too. Also, with the enrichment cache, do you actually put the enrichment data in with the? You wouldn't put it in the time series. I mean, it wouldn't sit on the side and you join it when you need it or something.
Okay, so the stitching happens actually at the time of polling. The polling plugin can actually choose to go out and get data from the device or actually use the data from the cache. So, but what happens is when the polling plugin is done, what comes out of this is a consistent model. Actually, I forgot, I didn't really touch upon that. We actually have well-defined internal models for everything. So, for example, taking the example of interfaces, when we collect interface metrics, no matter what platform, what version, what we're collecting interface metrics from, every plugin must produce interface metrics which has a certain set of metrics and a certain set of dimensions or tags. And those dimensions or tags could either come from the device or come from the enrichment cache. Does that make sense?
Okay, but I mean, it seems like extra if you're storing at every metric timestamp, all this metadata in the same place, that's kind of redundant because it's always the same or the same for days on end. Or
that is true, but most time series databases actually optimize that.
Oh yeah, right. Okay.
Yeah,
so they do it.
So
okay.
we count on essentially that. Yes.
Okay.
Well, and oftentimes the enrichments change over time as well.
Right,
so,
they do.
So you do want to store it with the source data so that if you do aggregations based on those, that you get an accurate answer.
Yeah. Okay. Yeah, that's a good point. Makes sense. Yeah. Thanks.
Hi, Aditya from Arista. Quick question on how granular is the timestamps on the time series graph? Is it millisecond granularity, 1 second?
We are collecting, so plugins, okay, because it's polling, it's not going to be accurate. Yeah. It is going to be the time when the data made it to the polling collection system. The plugin is configurable. There's a parameter called execute frequency, so as frequently as you wanted to collect the data. Currently in our production system, we have set it to collect to every 60 seconds. Okay. We could go down more for some devices, Arista devices, sure, but some of the other platforms, they just won't be able to handle the SNMP load.
Okay, thank you.
Which is why streaming telemetry has to come in.
I believe our backend supports 1 second resolution.
Yes.
But we poll currently at 60 second.
Also, just an implementation detail, the timestamp resolution is millisecond. Like, yeah, that's what the platform is capable of. Any other questions? Thanks, guys. Bye.
Thank you, Ian and Varun. It was a good talk. Take that. And before the next session here, we're going to have lightning talks, 3 brief talks. Before that, I want to remind everyone, last chance, please fill out the survey. We will do the final drawing, I think, in about 30 minutes. So please fill it out if you haven't already. That being said, our first lightning talk is going to be Brian Jeems. He's going to talk about PTP demands on the campus.
I'm Brian Jeems. I'm the network manager at the University of Idaho, and I wanted to talk about precision time protocol and the changes that's made for us in our campus network. really, we had no idea we were getting into precision time protocol 2 years ago. We just got a simple email request that, hey, we got this Dante-enabled classroom audio equipment we want to start installing. We need a dedicated VLAN. It needs to be a VLAN extended between 5 different buildings on campus. So that's pretty easy. Lesson 1 that we found out right away, hey, this doesn't work as expected if we don't have multicast. It needs IP multicast to work. So we had solved that for some other AV solutions. So add IGMP querier, PIM sparse mode. Seemed like things were good for a few months. Then, hey, we got major problems. Classrooms audio is cutting out all the time. And we're looking, we have packet loss. Is there some kind of network problem of a more typical variety? But turns out, no, it's the Dante protocol is going into election mode over and over again. Because if there can be only one. It's Highlander in the Dante world. There must be one master clock on this VLAN between multiple buildings. And so, here on the left is a happy microphone that's got latency below 2 milliseconds. On the right is an unhappy microphone that's seeing occasionally 5 millisecond latency. That'll cause it to kick off the election process. And the reason that's cutting out audio is that the microphones mute when they're doing the election. So it's going off all the time. What did we do about that? Well, quick and dirty solution. We have to solve this problem right now. We segment. So we pull the VLAN off the building trunks. You lose management ability, but the microphones are just fine working in with link local addresses, and every building has its own master clock. Everything's fine. We do a little more elegant version of that with a VLAN ACL, a few weeks later after we studied the situation. And really all we needed to do was block the P2P traffic in the core so that the buildings didn't see each other. And so each building could elect its own clock master. But now our classroom technology team's not happy because audio doesn't work between buildings. They were using that for monitoring. They didn't have any strong driver for it, but to monitor quality, to do troubleshooting, and for future needs to be able to have it, classroom sessions and audio into multiple buildings on campus. They wanted that to work. So we got busy. We kind of put it on hold until this summer and fall, and started working on the real solution. And for me and for my team, this was something brand new. I was talking with an engineer who had spent a good part of his career Monday at lunch in a wireless carrier network, and to him this was obvious. Hey, if you're doing P2P, you've got to have QoS. So we figured that out eventually, and so we just did in general, we've tried to keep the network real simple to operate, but we've added now QoS on the uplinks for any of the buildings with the Dante network. We're not quite there. We'll get there by the end of the month in terms of, right now we're down to 2 master clocks. There's one building that we haven't added QoS to that we've got to do a switch upgrade on. But then we'll be with everything running on one master clock with the full functionality the classroom technology team wanted. And just one more comment on the alternatives. A lot of the vendors, there's all kinds of AV vendors offering Dante equipment, and they recommend things like, oh, just build a separate network, totally separate switch infrastructure. Being a university, we like to be a lot more frugal than that, so that wasn't an option for us. And also, we could have made Dante subnets, one subnet per building, just kept it a layer 3 segmentation. The downside with that is then you want to do inter-building audio. Hey, here's some really expensive software you can buy that'll make that happen between subnets. Again, we wanted to go for the lower cost option than that and just keep it one flat VLAN around campus. And I just provided the Audinate reference link that has some of their reference details about this. So that's our story about P2P on the campus network.
Thank you, Brian. Our next lightning talk is going to be Alejandro Acosta. He's going to talk about V6 open resolvers.
Hello, well, good afternoon. Well, my name is Alejandro Acosta. I'm going to talk to you about a project that in LACNIC we feel something like proud about this. Basically, it's identifying DNS open resolvers, as you can see in the title, which is quite specific. Well, as all of you know, to identify DNS open resolvers in the IPv4 world is quite easy because the IPv4 address space is not that big. In IPv6, it is more difficult, and we needed to take a different path. So, what we did? Basically, we are taking, with a very specific TCP/DOM command, we're creating a pickup file in a root server. Actually, this is a reverse DNS root server. It is not the root server that traditionally we listen, but it is somehow a server that receives a lot of queries. The queries that are getting that we can identify in step 1, we can safely assume that are recursive servers in the internet. So what are we doing after that? After we have the pickup file, we process it, we work with it. We are using PyChark to do this. We remove in somehow duplicates and IPv6 addresses, and so on. Then, after we have the IPv6 address identified, which we know that it is a recursive DNS server, we perform a very simple query trying to see if that IPv6 address allows recursion. Okay? This is actually the way that we identify IPv6 addresses. I am doing some emphasis here because traditionally when we present and we show this project, the main question that we receive is how do you identify the IPv6 address? There are many other ways of doing this. And well, finally, the last step, of course, is processing the data, showing results, publishing, and so on. I'm going to skip this slide since the results, I'm going to show most of this. OK, there is a summary. Maybe this slide is interesting. You can see by RIR the total of IPv6 DNS server that we have identified. For airing, let's talk only about the first line. We have identified almost 2,000 IPv6 DNS servers. What we did, we ran a simple query to all of them, and we were able to get 51 open resolvers. Okay, as all of you know, maybe this is not the expected behavior. Most of the time, open resolvers are not good in internet. Of course, we know that some providers in somehow have DNS recursion enabled to everybody, like Google and many more. So what else? This is more or less the same information that that was shown in the table. Let's talk one more time about ARIN, since we're in ARIN region. In the most left bar chart, you can see in the blue line the total number of servers that we have found, and the orange line more or less shows the DNS that were open in somehow. Okay, it is allowed recursion. This graph, it is only for LACNIC region. Sorry for that. I did this slide last night. Since we are getting data since March of this year, we were able to create a timetable. However, we can do this for any RIR and for any country, actually, that we wish. Basically, you can see that on the first graph, the amount of open DNS resolvers, IPv6, that we have found in our region, in LACNIC. And in the second graph, you can see the evolution of the non-open DNS servers that we have found. Later, you can see that Brazil, they have the most amount of DNS servers, and the same case for open resolvers in IPv6. And we have found something that is interesting, at least from my point of view. We have identified that certain /64 prefixes, there are a lot of resolvers in each. For example, in the first line, we found 62 servers in only one /64 IPv6 prefix. We believe that this is because of the privacy addressing that some operating systems have implemented. But this is, from my point of view, this is quite interesting too. What were we looking for? This is type of results that we have. You can see at least yesterday I did this, a couple of ARING results from Canada and from the US. I only took servers that we were able to find that were closed. On the very right, just on the left of ARING, we were able to get the owner ID of that IPv6 address. So after that, we were able to contact the owner of that IPv6 address and tell him, or tell them, sir, you have an IPv6 open resolver, please take care of that. And this is an example of what LACNIC members, only LACNIC members, are receiving in this moment. This is an email that we started sending about 6 weeks ago. You can see that every Monday, you can see something like, dear member name, you appear to be running a DNS open recursive resolver at IP address, blah, 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 blah. It explains what it is. There are 2 examples in how to fix this for bind and unbound. And I'm happy to tell you that we have already got evidence of people that receive our email and fix their server. Actually, we have a very nice example. Last week, one member of LACNIC received the previous email. He had 2 servers. Of course, we only found one of them, and the member fixed the 2 servers that they have. So it is a very interesting example that now we were able to do this, and we are very happy. We are not sending the email to other regions, for RIPE, Afrinic, or any other one. If you wish to contact us in somehow to go in detail how we are doing this, please feel free to contact me. Our next steps is integration with some LACNIC systems, when the user enters username and password, automation of some statistics, publishing open data. And something that we think could be quite interesting is trying to find out if some of the DNS servers that we were able to find probably are in squat prefixes, prefixes that has not been assigned by any RIR or IANA even. And that's all what I have. I don't know if there are time for questions. Oh, hello.
Good? Okay. Wes George with ByteGrid. I'm curious, did you see any 64 addresses in the analysis you did?
64 addresses? You mean map ID addresses?
Like 2002::/16.
Ooh, actually, that's a terrific question. Unfortunately, I did not pay attention to that, but I still have the data. So I'm going to do it now that you mentioned that.
I might suggest that you look at that because I was analyzing earlier this year, I was analyzing a V6 DNS dictionary attack for a large DNS provider. And out of, let's see, out of the 400 or so open resolvers that I found out of the list of querying hosts that were participating in that dictionary attack, more than half of them were from 6-4 space. And I couldn't really determine whether that was some sort of weird vagary where, because there was a 6-4 functional address, the DNS server was just doing that because it was configured and it was using whatever available interfaces, or if there was some sort of an explicit effort there, or if this was more, the two were unrelated. Like you had a v4 open resolver that also had a 6-4 address and was talking via that interface. But there's probably some analysis to be done there, because one of the questions that might come out of this is it time to just start configuring authoritative and recursive DNS servers to reject queries from 2002::/16 as sort of overtaken by events and no longer useful, and thus just closing down an attack vector? I don't really have a good answer to that, but that's the question raised in my analysis.
Well, terrific, interesting. Believe me, I'm going to my computer and I will try to find the list of IPv6 addresses regarding that 6-4 transition mechanism.
And if you want to see the data on mine, if you go to iepg.org, it's in the March 2018 presentations.
Okay, let's talk about that later. Thank you. Bye.
Thank you. Thank you, Alejandro. Thank you. So our final lightning talk speaker. Thank you for doing that. Yeah, that's right. It's going to be Ignas Bagdonas. He's going to talk about the end of VXLAN, or sunsetting.
Hello there. So for the end of the event, let's discuss one topic which has been quite much beaten over the 3 days, VXLAN, and what is happening with that. So just a small note to other fellow presenters. Please be careful with your spelling. That abbreviation is all 4 capital letters, not in other way. So the history of VXLAN. It was a successful accident, in fact. Around a decade ago, one particular vendor was working on a particular family of the products, and they had some set of requirements to be able to carry Ethernet frames over IP transport. So it was designed with certain tradebacks, knowing that this is not a universally applicable solution. It was not part of the IETF working group process. Eventually, it came to the IETF as an individual submission and was mostly there for documentation purposes. It actually took the world by surprise. It was simple enough, and to this day, it is the most popular encapsulator for carrying general layer 2 payload over IP. However, that encapsulator is starting to show off its limitations. And the limitations are 3 large families. One thing is there's no possibility to indicate the type of the payload. Whatever gets into the tunnel at the other end is received as is without any indication. There is no way to indicate that the packet which is being sent is not the actual client packet, but something else. And the worst of those, which would be able to solve those 2 problems, is that there is no extensibility in the protocol itself. So the protocol identifier. It is assumed that what is carried over VXLAN tunnel is an Ethernet payload. And if you need to have a further demultiplexing, you need to carry the protocol identifier in the payload Ethernet address, or use some other internal encapsulator within that in order to be able to demultiplex that. Certainly that can work. That's not the easiest or say the most flexible way to do that. Now, one possible solution which is used in practice is to run parallel tunnels. That certainly works, and the namespace for the VNI identifiers is sufficiently large enough. However, there is another practical problem. The cost of the tunnel itself as an entity on the element is far bigger, and that is a far bigger practical problem than the perceived depletion of the VNI identifiers. Non-client payload. There's no ability to send out a packet, a frame, which does not belong to the client, and consequently, there's no ability at the other end for the client to distinguish that this packet is actually not a client packet, but something else. And this basically rules out a majority of the traditional OEM mechanisms which we are familiar with. For example, running BFD over VXLAN tunnel is definitely non-trivial. There are workarounds of doing that, but if we want to compare that to equivalent of the MPLS equivalent solutions, that's just nowhere near. And all sorts of OEM and non-client payloads, they assume that the client is aware of that and cooperates. So if you have a scenario where you want to validate the liveness of VXLAN tunnel, this assumes that the client itself needs to be aware of that BFD session. It's not necessary enough to terminate a BFD session only on the network element itself. VXLAN is not extensible. All of the fields, all of the values in the fields, they are predefined, and if we are talking about the interoperable extensibility, it is just not possible. This results in various proprietary extensions. Yes, such things do exist, and we certainly cannot talk about multi-vendor interoperability in this environment. It was becoming evident that such type of encapsulators, they are popular, they are solving practical problems, and therefore industry overall needs a more flexible and interoperable solution. IETF started a dedicated working group, Network Virtualization Overlays over Layer 3, around 2012 timeframe. And the major requirements put up front that group were to develop an similar or equivalent encapsulator which had the extensibility, multi-vendor extensibility, which would be hardware friendly. Again, we are talking not only about the software implementations, which are easy, but we are talking about the hardware-only implementations for which variable length structures and all sorts of field manipulation are really costly. There were concerns being raised about the lack or the complete lack of security aspects in VXLAN, and also ability to implement that in practical terms by the majority of the vendors, not only a selected few. And what resulted? There were a multitude of proposals. Three main ones: Genève, this is actually not an abbreviation, this is the name of a protocol. GUE, generic UDP encapsulation, and direct and semi-backwards compatible extension to VXLAN, the VXLAN generic protocol extensions. GUE was perceived to be too complex. It's a flexible one. It provides a lot of functionality, but to implement that all in hardware was seen to be too complex. And the backwards compatibility nature of GPE was seen to be too limiting for this protocol to be future-proof. There were some niche protocols and proposals. They did not advance too far. So Genève was seen as a compromise between the extensibility and the ability to implement that in, well, practical systems. So today, if we are looking from IETF perspective, the direct successor to the VXLAN is Genève. What that protocol is and what it does. It's an extensible encapsulator able to carry different types of payload even at the same tunnel. It has ability to signal that some payload being carried does not belong to the actual client. This is a service payload. It has ability to do integrity check on the header itself. This is to limit out the possible attacks of injecting stray Genève packets into the network. It has ability to encrypt the payload if that is considered to be needed. And it allows roughly for 250 bytes of vendor extensibility space and does that in a manner which is interoperable with, among the vendors. It simply uses the vendor's PCI identifier to indicate vendor-specific extensions. Oh, it looks like VXLAN is just a better VXLAN. So what is important if you are designing a new, especially new environment which uses these types of encapsulators? If OEM and interoperability is important, VXLAN is just not an option. This doesn't mean that VXLAN is completely unusable and broken. If you are in a single vendor environment and you are happy with rather limited ability of OEM tools, that's definitely fine. If you are looking into something more complex and more future-proof, Genève is the right way to continue. The current state of the industry is that majority of the relevant component vendors do have either shipping or sampling support of Genève in their products. System vendors are getting there. It's some are in trials, some are in prototypes. And what is mostly now needed and required from the community is to start looking from a design perspective. If you are looking into the overlay type of designs, seriously consider VXLAN as being obsolete. This is only about the data plane. No changes in the control plane, so your favorite EVPN or whatnot you are using stays exactly the same. The only change is that the encapsulator used for tunneling your payload is now different. That's it from my side. Thank you.
We have time for a question or two, if you have it. Otherwise, thank you, Ignas.
Right, thank you.
So before we close, first, on behalf of the program committee, I want to say thank you to all of our speakers. I think we had a pretty good week so far. And I want to announce the final survey drawing winner. Andre Kosten, or Costine? Thank you. I'm always glad when the winner's here, because otherwise we have to figure out backups. So, and with that, I'm going to turn it over to our Executive Director, Edward. Thank you, Edward.
Just so I stay on course. So first of all, I want to talk about the election results. So as kind of a recap, the amendments for 2018, the updates were approved. We have retiring board members of Ryan Donnelly and Dave Timken. And I'd like everyone to kind of give a round of applause for their service to our community. I know personally they were very, very important to my onboarding process, and I appreciate the support they've given me as I've been on NANOG as Executive Director. We have new board members, which are Susan Forney and also David Siegel. We have a new, they didn't put in the information, so I'll just tell you. We have a new chair, that's Sean Kennedy. Our new vice chair is Tina Morris. And our new treasurer, our existing treasurer will continue, Will Chernock will stay in that role. And then finally, Susan will be joining us as treasurer. Secretary, sorry, thank you, secretary. Will's treasurer. And I'd like to take a minute and talk about membership. For me, as executive director of NANOG, if I had kind of one thing that's kind of my thrust, that North Star that I try to focus on, and that's really thinking about the future of NANOG. I want NANOG to be around so that if my grandchildren decided they wanted to be members of NANOG, it would exist and it would be relevant. So my thrust is that. And I actually call upon members and non-members alike that being part of NANOG is about seeing the future of NANOG, seeing something that exists beyond us, something that will outlive us, and something that will be a strong contribution to our community and the world beyond. In a modern society, the internet is the very foundation. There are entities that exist now that never existed before prior to the conception of the internet. And I believe that all of you here are part of the keepers of that, who make that happen and make that a reality. And your participation within NANOG is critical to assuring that these kids here may someday become members of NANOG and that it exists and it's relevant for them. Now, the other kind of converse to that, which I think is the most dangerous, is indecision. If we sit back and we expect someone else to take the front, we expect someone else to take the lead, someone else to make a difference, then we are going to become victims to indecision. And indecision is never good. I had an old boss who always used to say to me that indecision is a decision in and of itself. That saying, why did I think someone should become an active member? You help us deliver meaningful content to the community. You help us govern NANOG in a reasonable and responsible manner. You help us create a sustainable community of inclusion and diversity. And finally, you help us to build an organization that will outlive all of us. Now I'll get into the customary meeting stats. So we had 940 attendees at the meeting. Member registration was 249, students 9, speakers we had 20, college immersion 21, female attendance 12%, and countries in attendance 21. Our top organizations, NTT, Oracle, Cisco, Microsoft, Aaron, and Nokia. Organizational demographics, service providers made up 40%, vendors 21%, data centers 10%, IX network operators are 12%, nonprofits 10%, and others make up 7%. Special thanks yous. I'd like to first thank our hackathon sponsors, Oracle and Tessuto, and our premium and host sponsors, TechSavvy, our host, Telesis, our connectivity sponsor, Netflix and NTT Communications, our diamond sponsors, Amazon, Imperva, Microsoft, and Oracle are platinum sponsors, and Sixtera, Google, and VeriSign are gold sponsors. If I butchered any names, I'm very sorry. Special thanks to our meeting sponsors. And then a very, very special thank you to you, the members, for supporting us, our board of directors, our sponsors, and a special thank you to Valerie and Day. Without them, this would not happen. There's been some changes. Day Harvey is responsible for making this meeting happen, and she's done a marvelous job. We could all give her a round of applause. And Valerie was an invaluable assistant to the program committee for making all of this happen. So again, applause for Valerie. So did you all enjoy the social last night? Good. Special thank you to Lisa for making that happen. I would also want to thank our contractors, iMiller, Clarity Experiences, Linespeed Events, Cascadian, and Riverbed for putting all together our technical support, and for the Hamilton Group, Christian Perry, Tessa Overfelt, and Sabrina Hazeltine for helping to put all this together, little background stuff to make everything happen. That said, see you all in San Francisco. Thank you for coming.